right. Hey, everybody. We are back with what we will call part 2 of our discussion of the model specification process. So this follows material from chapters 6 and 7 in our Studenmund textbook. And just to remind ourselves, part 1 of this discussion had to do with the implications of omitting an important variable from your regression. And the implication is potentially biasing the remaining coefficients, right? So the lesson obviously was do everything you can to think through the theoretical data generation process to gather data to match those variables that should belong in the regression, and then make sure you go through your hypothesis testing, your diagnostics, to include only the variables that belong, but don't leave out any that should be there. So our discussion is going to follow on from that by introducing, by reminding ourselves about dummy variables and then introducing the concept of the slope dummy variable and the interaction term in general. And the way in which this is a follow-up to that previous discussion is it's not obvious how these variables that we might have in our data set, that we might have in our data generation process, influence that dependent or y variable, that we can think about kind of indirect effects, how a variable x might affect y through a variable z, for instance. And if you don't think that through, and if you don't know how to include those interaction terms in your model, well, guess what? You've omitted important variables and you're right back in the omitted variable bias issue. So let's start off here by reminding ourselves about the basic dummy variable, right? And we've seen this before, right? So a dummy variable is a binary indicator capturing the effect of a discrete characteristic, right? The answer to a yes or no or a true or false question. And we like to think about the inclusion of a dummy variable implicitly separates your sample of observations into the treatment group versus the control group, right? And the way we've seen this up to now, it's been as a quote unquote intercept dummy, right? Where the treatment group is going to have the same slope, the same marginal effect of x on y, but a different intercept. The average value of the predicted y will be different across the two groups, higher or lower, depending on the sign of that dummy coefficient. So the way we're going to change that is introducing this idea of a slope dummy, where rather than separating the control and the treatment group into two parallel prediction lines, well, now we want to see if the marginal effect differs from one group to the next, if the slope between an x and a y variable depends on the condition, right, the characteristic of interest that separates the treatment versus a control group. And once you kind of start to think in these terms, once you have these sorts of variables in mind, you will see them everywhere, or at least the potential for them everywhere. Every time you see a dummy variable, you're going to ask, should that be interacted with an x variable? Should that be indicating a change in the slope rather than simply a change in the intercept? So remember, with the intercept dummy model, really all we did is included that binary indicator variable, right, as an additional regressor, right? So the notation, if you recall, right, so the B1 term here is the marginal effect of x on y, where x is a continuous explanatory variable. The DI here is the 0, 1 dummy indicator, and the delta 0 is the magnitude of the shift, right? That is the dummy coefficient. And again, the way we think about this is it gives us two separate prediction lines. So for the control group, for which DI is equal to 0, well, of course, that term drops out and you're left with the intercept of B0 and the slope of B1. For the treatment group, where DI is equal to 1, indicating, right, those observations contain the characteristic of interest, whatever that may be, the slope is still the same. It's that B1 term, but the intercept is altered by that delta 0 coefficient. So we get the intercept shift effect by the magnitude of that delta 0 term, which, as we saw, can be estimated via OLS. We would get a delta 0 hat, and that would represent our model's predicted change in the mean between the two groups. So, reminding ourselves again what this might look like. If we imagine a case where that delta zero term is positive, the original intercept is positive, and the xy slope is positive as well, this is going to be a parallel shift upwards, right? So if you could imagine a silly example, if we're trying to predict income based on education, well, we might want to control for whether or not that education includes an economics degree, right? And of course, the B1 is going to be positive. Y could be income, it could be happiness, it could be awesomeness. It's going to be positive either way. We're going to see that parallel shift upwards here by the amount of that delta zero. Okay, so again, we've seen that before. We've got our two separate prediction lines for the treatment group and the control group. We're good to go. And thinking about another example, say if we want to predict income based on education again, but control for whether or not an individual has a criminal record, probably uncorrelated with whether or not you have an econ degree, we might expect, all things equal, that delta zero to be negative, right? And our picture would look like this, right? So the picture is exactly the same, just the direction of the shift based on the sign of that delta zero now is going to be a downward shift comparing the control group versus the treatment group. And again, the treatment is the observations with the value of 1, possessing the quality of interest here, having a criminal record. But again, in these examples, the lines are parallel. Is that actually realistic? Well, to answer that question, we will need to test the significance of the slope dummy variable. And here's where things get interesting, right? So as we see here, it's often interesting to look not only at the impact of a given quality on the mean outcome of y, but also on the marginal effect of x on y. Is the slope of the regression line different for the two groups? Male versus female, white versus non-white, econ degree versus non-econ degree. The effects of those qualities, right, can be more subtle than just affecting the mean value of y. They can affect how many continuous x variables influence the outcome of interest. So I think in the previous example of dummy variables, we looked for evidence of gender discrimination in a wage determination model, right, where predicting wage as a function of education and gender, we saw, unfortunately, evidence of discrimination. That line was shifted down, but that's not where discrimination ends, right? It's a fair question to ask, right? Does an additional year of education have a smaller effect on wage for females versus males, right? Not only is your average wage lower, but the return on education might be lower as well. Well, the question now is, how do you include something like that in your regression model? Well, we're assuming for the moment here that the intercepts will be the same. We can add that back in just to focus in on what we're talking about, focusing in on the slope here. So let the slopes differ, but the intercept be the same for the moment. The crux of it is, again, going to be the existence of that binary dummy variable, the di equal to 0, 1. But now, instead of including it just on its own, we are going to interact that variable with one or more of our continuous x variables. So anytime in the context of a regression model, we see that phrase interaction term, it's going to mean the product of two variables. So here we're going to look at the product of a continuous variable x and our dummy variable di. And that interaction is going to give us this complementarity effect, if you will. One variable affecting the impact of the other, strengthening the effect or weakening that effect. Okay. So let's write out the regression equation again. So we've got yi equal to b0 plus b1x, so that's kind of the baseline model there. And again, we have the di term in the model, but here interacted with, multiplied by that continuous x variable, and the coefficient now we will denote as delta 1. So remember, the delta 0, the notation was handy, right? The sub-0 matched up with the sub-0 here, so that indicated it was an intercept augmentation, shift up or down. The delta 1, the 1 subscript, indicates that it's going to be an augmentation of the slope term, the B1. Okay. And just kind of walk through the same logic, right? It's an either or proposition. That DI term is either going to be 0 or 1, so we can trace out the resulting prediction line in either case. So when DI is equal to 0, again, it doesn't matter if it's interacted with X or not, that whole thing is going to drop out, and we're left with that baseline regression. Slope of B1, intercept of B0. And the partial Y, partial X is going to be the B1, estimated as B1 hat here. Now for the treatment group, the DI equal to 1, we'll just plug in a 1 for the DI, and essentially what happens is X now appears twice. So the slope of X, the impact of X on Y, is going to be the combined effect of these two coefficients. And the augmentation here, that delta 1, is only going to apply for the control group, for the subsample, right, that contains the quality of interest. So the partial Y, partial X is now going to be a little steeper or a little flatter, depending on the sign and the size of that delta 1 term. I know, pretty cool, right? And we'll walk through some examples, but just keep in mind that you can interact a single dummy variable with multiple continuous variables, right? So a more realistic model might have B0 plus B1 X plus delta 1 X times DI plus B2 times Z plus delta 2 Z times DI, right? So that same dummy variable can augment multiple slope terms. And this is where the artistry of econometrics comes out, right? Because we've got to think through where these effects are going to show up. There's no guidebook, right, for any data set telling you, oh yeah, you need to interact this, this, and this. The researcher has to think that through. Okay. So again, the good news, just like the intercept dummy effect, we don't need to do anything fancy here. We estimate it just as if it's any other additional regressor, estimate it via OLS. We apply our standard hypothesis testing. We look at the t-statistic, right, before we decide if it belongs in the regression or not. Kind of awkward the way I put it in the slide here. We only impose the interpretation if you can reject the null of 0, right? Meaning we only actually think that there's an augmentation steeper or flatter for one group or the other if it's a significant coefficient. So as always, think about that using the t-statistics as a coefficient by coefficient, variable by variable specification process. Does it belong in the model? Does it help explain our variation to Y? Yes or no? And if it does, you leave it in, and then you can tell that story of the augmentation to the slope. And just as a quick note here, if you actually create these variables, like generate a new variable that's the product of the dummy and a continuous variable, and then you actually open up the data browser, don't be alarmed. It's going to look a little odd, right? You're going to see a bunch of zeros in your data set for when the DI is equal to 0. And then in the same column, you will see continuous variation, which is going to be the value of X when DI is equal to 1. And so you can kind of overthink it a little bit. You would look at that column of numbers and you'd say, what does this represent? Well, just take it back to the derivation of the equation of the model, right? It's representing the augmentation effect due to the binary dummy variable. So just for the sake of the visual here, let's imagine a case where we have a positive intercept, a positive baseline slope, and a positive interaction, a positive slope dummy coefficient. That delta 1 is positive. So what that's going to mean is that the impact of X on Y will be larger for the treatment group when DI is equal to 1. It's going to be a little bit steeper by the value of that delta 1. So we can think of any number of examples here. This one isn't necessarily obvious that it's going to be positive, but if we're doing kind of a capital asset pricing model equation where we're predicting the return on a given asset, so stock return on different firms as a function of, say, the S&P 500, the market return, and doing this in a cross-sectional regression, we might want to control for industry effects, right? So we can generate a series of industry control dummy variables. And let's say we have the variable DI equal to 1, indicating that the firm in question is a financial firm. Say it's a bank. And say bank stocks tend to be more sensitive, they react more strongly to a change in the overall market return. This would be the picture that would result, right? So we have our treatment group here, banks, they've got that steeper prediction line. Non-bank firms would have that flatter line, but still positive, right? And the difference in the slope is going to be that delta 1 term. And again, we're, for better or for worse, kind of keeping this simple, just focusing on that slope effect. But note that we could, and maybe should, also be including the dummy variable on its own, right? So is there a shift and a pivot, a shift and a change in the slope? That's definitely possible as well. But just focusing on the interaction term. And then when that delta 1 is negative, holding everything else constant, we're going to see, right, a move in the other direction. The slope of that line is going to decrease. That line is going to be flatter for the control group versus the, sorry, back that up. The line is going to be flatter for the treatment group relative to the control group. So another kind of off-the-cuff example here. Let's imagine we're trying to predict country-level GDP growth as a function of dollar value of foreign aid inflow. So trying to model the effectiveness of foreign aid in developing economies. We might want to control for the political environment. So if country I is a non-democratic government, the value takes on the value of the dummy variable takes on the value 1, and that's going to be our treatment group. And the expectation would be perhaps that the foreign aid inflow is going to be less effective. The marginal effect on GDP growth is going to be smaller, and it would look something like this, right? So we have a steeper line for the control group, a flatter line for the treatment group. Cool. Okay, let's actually see what this would look like with a little example in Stata. And let's go back to the gender discrimination case in a wage determination model. And we want to do that, kind of answer that question. Is there an impact of gender on the return to education? So not just an effect on the average wage, but the marginal impact of that extra year of education. So first thing, we need to construct that slope dummy interaction term, the product of our two variables. And there's an easier way to do it, but this way you'll never get it wrong, right? Think of it that way. So we can use the generate command. We're going to create a new variable called, somewhat clumsily yet descriptively, education underscore female. So we're interacting those two variables, and it's just the name of the X variable times the name of the dummy variable. So education times female. And that, again, is going to be our new variable. It's going to pop up into the variable list in Stata. And when you actually open it up, it's going to be zeros for the males, and then for females, it'll take on the year value of education. Okay. So once we have that created, we just add it in as an additional variable in our regression command. So if we're going to regress wage as a function of education, say work experience, and then this gender effect through the education variable. So not just the female dummy variable on its own, but interacted with the continuous education. And again, in this case, just to keep it simple, I'm only including the slope dummy term, but you certainly could include both the intercept shift effect and the slope dummy effect. It'll complicate things a little bit. It'll introduce some multicollinearity because both of those variables are going to have the same kind of root variable of the gender dummy. So they're going to be highly correlated with one another, not perfectly correlated, so not violating our assumption 6, if you recall. But it'll be a little bit more difficult to interpret the results. not to worry, chapter 8 will give us a way to think about that. But that's kind of the reason that I'm leaving it out. So you run the regression and we get some numbers, and I just wrote it out here as an equation form. So we get an intercept, negative 5.66. The slope on education is 0.87, so that extra year of education adds about 87 cents to your wage, holding all other variables constant. Every year of work experience adds about 15 cents to your hourly wage. And then we get this guy here. So this negative 0.15, the coefficient on the interaction on the slope dummy, that is the delta 1 hat. Sorry, that should have a hat on it there. That's our estimated coefficient. And p-values in parentheses, p-value of 0.01 indicates that it is significant. We can reject the null of 0 with 99% confidence. But what does it mean that it's negative? Well, that positive slope relating education to wage is going to be a little bit flatter for the treatment group, which in this case are the females in the sample. And specifically, each additional year of education will add 15 cents less to your hourly wage for a female relative to a male. Okay. And when you are asked to interpret the results, that's what it's going to come down to. What is the difference in the marginal effect? So for the control group, it's the B1 hat, the 0.87, that baseline slope. For the treatment group, it's the B1 hat plus the delta 1 hat, which in this case is going to shave off that 15 cents per hour. So that gives you the treatment group marginal effect of 0.72. All right, and the picture that would come along with that would look something like this. So this would be the control group versus the treatment group. And again, we're assuming that there is no effect on average wage because we didn't include the dummy variable on its own. So they both have that negative intercept, the B0 hat here. And yeah, that seems a little bit odd at first. We talked about this before. Really what that means is you need some minimum number of years of education before you can start earning a positive wage, before you can start climbing up that little wage line. And equally, kind of an equally depressing interpretation is, well, for males, you can start working when education hits here. For females, the predicted kind of minimum level of education to start earning a positive wage is going to be higher. And for each year of education that you attain, you get a smaller rise in your predicted wage. So sorry about that. But that's what the interpretation is going to be. So be able to work this, as we say, backwards and forwards, right? If a question is proposed, does education have the same benefit to males versus females? Be able to link that with the regression that you would run. What do you have to interact? And what would that regression look like? And then the other direction would be, if given the output, if given this equation, be able to interpret this coefficient, right? Once you recognize that this is an interaction with a dummy variable, then you're going to know what to do. All right. So I mentioned that creating that dummy variable interaction with the generate command is one way to do it. It's kind of the can't miss way to do it. There's we can be a little bit more creative in Stata, both in running these regressions and in looking at the results. So we can show some Stata commands to streamline things a little bit here. And the first thing we're going to show is this. The little hashtag essentially is the interaction operator in Stata. So we can get exactly the same results that we just saw by running this regression. So wage, and then on the right-hand side, instead of education and the product of education and female, we do this double interaction operator. Another thing is we have to use this C dot prefix on the education variable. That is telling Stata that this is a continuous variable. So the C dot says, okay, we're going to treat education as a continuous variable. I don't have that continuous indicator on female, so that's going to be the binary variable. And then the double hashtags, the double interaction operator says include education on its own and the product of the two. And then we're not interacting anything with that extra experience variable here. So that's one way to streamline the regression. You don't have to kind of clutter up your data file with all these newly generated interaction terms. You can create them within the regression command and then get the results, but the variable actually hasn't been added to your data set. Then the really cool thing is after running a regression using that interaction operator, so Stata knows, right, that we're going to be looking at a change in the marginal effect due to this interaction, we can create exactly what we want, the slope of that line at different levels of education and the dummy variable female, right? So this margins command at, and then parentheses, education equals 0, 1, 18. So that means we're going to calculate the marginal effect for all values of education between 0 and 18, changing at 1 unit increments. So depending on what your data looks like, right, what the minimum, what the maximum might be, and what those changes in between are going to look like, we can specify that here. And then we're going to do this for 2 different plots, right? 2 different lines, one for female equal to 0, one for female equal to 1. So we're going to arrange that from 0 to 1, changing at 1 unit increments, meaning just 0 or 1, right? Then you follow that construction. So this is going to create, basically calculate behind the scenes what those marginal effects are going to be. And then the margins plot command is going to, as the name implies, create the graph. It's going to plot out the margins created in the previous command. And it's going to look like this. So a little bit prettier than the hand-drawn version. Also includes the 95% confidence intervals in these bands here. It's the visual here, you can't pick it up real clear, but we can see that the lower line, right? So that's the shift downward because of the female dummy term on its own. And it's a little bit flatter. That's the part that's a little bit hard to see. But that difference in slope is going to be coming from the interaction term. So you can create all of this with multiple predict commands and a 2-way scatter plot command. But this will do it for you. So you can, as always, try to tell a story with some data visualization. This is a nice way to do it. Okay. So get some practice with that. So shifted down and a little bit flatter. Okay, so that brings us to what we'll call the general interaction term, right? So the slope dummy term interacted a binary variable with a continuous variable. Again, that kind of indirect effect. Well, there's no reason why one continuous variable can't influence how another continuous variable influences the y variable, right? Again, think about it as a complementarity effect. As one variable goes up, does it make another stronger or weaker in its explanatory power, in its influence, its impact on the outcome in question? So now that we've got the idea of an interaction term, again, we're just going to generalize it here. So capturing the change in the marginal effect of x on y due to a marginal change, a 1-unit change in a third variable, z. So I say here a second variable, a second explanatory variable, a third variable overall if you're counting x, y, and z. And again, here it's going to look exactly like the slope dummy effect in terms of how we create the variable and put it in the model, but z now doesn't have to be a dummy. It can be a continuous variable as well. Okay. And the trick now is that we're going to be presuming that the coefficient, the marginal effect of x on y, is going to be itself a linear function of z, be it positive or negative, right? But the effect of x on y changes as Z goes up and down. So let's take a look at the model before we think about some examples here. So our model starts off as plain as can be, right? So we've got our intercept. Sorry, I changed notation on here. Intercept, call it alpha. The baseline slope here we'll call beta times x plus our error term. But here is the interaction assumption that, just like we said, the slope, the marginal effect of x on y, is a linear function of this additional variable z. So we've introduced now two new coefficients, a beta 1 and a delta 2, all within this marginal effect term. Make the substitution, right? Plug this in for beta and multiply it out, and look what we get, right? The intercept, the slope of x on y, and then the new coefficient, the delta 2, is going to be the coefficient on this product of x and z. Just multiplying this out. And that's going to be, right, playing the role of that slope dummy effect. That's the augmentation. But now, rather than just being it's either flat or steep, it's going to be, right, a continuous range of variable, of slope terms, of marginal effects. Every different value of z is going to give you a slightly different predicted effect of x. So we can no longer have, right, an either or situation. The slope term, partial y, partial x, just like we started with, is this linear function. And what that delta 2 is going to represent is a second derivative, right? The effect of z on partial y, partial x. Does z make x more impactful or less impactful on y? And the same story that we had before, right? Once you start to think in these terms, the more often you're going to see the potential for these variables. So if you have, you've got a data project you're working on, you've got a y variable, you've got 4 x variables to deal with. Well, now you've got to think about each one of those explanatory variables as a potential partner with each other variable, right? Are there these second order effects within your data, within your data generation process? Again, your data set's not going to have an instruction manual telling you which variables to interact with each other. We've got to think it through, test the implications, test the significance of these interactions. Do they make sense? Do they tell a compelling story? Lots of fun. So here's a quick example. The old classic Keynesian consumption function typically just has consumption as a function of disposable income. The slope of that function is the marginal propensity to consume. But a good question is, does that marginal propensity to consume for different households change as the wealth level changes? In other words, not everybody has the same slope of that function. Is that a hypothesis that we can test, a result that we can look for? And just playing around with a toy data set here of 30 cross-sectional observations. So household level income, wealth, and consumption data. What would this model look like? Well, it starts off looking like, Econ 101, consumption function, consumption as a function of income. But that beta term here isn't assumed a constant fixed value. It's assumed to be a function of z, in this case, our wealth variable. So just like we did before, make the substitution, and we now have our baseline slope plus the potential of this interaction. As wealth goes up, does that change the impact of income on consumption? And the magnitude and the sign of that effect is going to be represented in that delta 2 interaction coefficient. Okay. So we can do this again, essentially the easy way, the can't miss way. Use the generate command in Stata, create a new variable combining income and wealth. So it's just the product of the two, and Don't have to do anything fancy. You don't have to tell Stata, right? Oh, this is an interaction term. You just throw it in there as an additional regressor. And we try to interpret the coefficient. So we have what we could call the baseline level of the marginal propensity to consume, the slope here of about 0.71. And then we get a positive and significant at 1% delta 2 coefficient, the coefficient on the interaction between income and wealth. So again, if this was your econometrics final exam, you see this regression, and the question is going to be, what is going on here? What does this mean, right? And the trick, of course, is recognizing that it's the coefficient on the product of two variables. So this coefficient is going to be augmenting this slope term here. And just as a quick note, we could once again use that interaction operator in Stata. So we could run the equivalent Stata command for that regression, regress consumption as a function of income, and the interaction between two continuous variables. So we got the C dot income, hashtag interaction, I should say, C dot wealth, and it'll come out exactly like this. And just to make clear, if I did the double interaction term here, then it would want to include income on its own, like we have here, wealth on its own, and the product of the two. So if you just want to include the product, like we have here, use the single interaction operator. Okay, so what does all this mean? Be able to put all this into words with some facility. So the interaction coefficient, that delta 2, is positive and significant. So once you hear that, setting the magnitude aside for a second, what does that mean? As wealth increases, the impact of each dollar increase in income has a larger effect on consumption. The MPC rises as wealth increases. Putting the numbers into our marginal effect equation, so the baseline, the beta 1 hat, plus the interaction coefficient times wealth. So if you have zero money in the bank, if your wealth is zero, your marginal propensity to consume is predicted to be 0.71. And for every extra dollar in your bank account, asset holdings, your wealth goes up by $1, that slope creeps up just a little bit by 0.000011. And notice we had the, everybody loves their scientific notation, right? So 1.14 E06. So we have the 1 starting on the 6th place after the decimal. So 5 zeros and 1 1. And of course, the reason why that number is so small is because $1 in wealth isn't expected to have a big effect. So it might be a good idea to scale that up, right? Say, well, okay, what if one person has an extra $10,000 in wealth? Well, now that's going to have a noticeable effect on the marginal propensity, right? It's going to increase by this times 10,000 or 0.01. So every $10,000 added to a bank account is going to pivot up that prediction line, increasing that slope by 0.01. All else held constant. So this presents a little bit of a challenge in the visualization because, again, the way I drew it here, there are just two lines, but in reality, right, every household was going to have a different value of wealth, and every household, therefore, is going to have a different prediction line. So it's not just a treatment versus control, like a flat versus steep. It's a continuum of different positions there. But you might want to pick out just a few of them. So again, at wealth equal to 0, we get that flat line, the slope of 0.71. And then at a wealth level of 100,000, we add about 0.01 times 10 up to about a 0.81. Right? But the idea being an increase in wealth might not directly affect your consumption, but it indirectly affects it through the marginal propensity. Okay? Another way to visualize this result is just to directly plot out the marginal effect itself as a function of wealth. So you're basically plotting right? The slope of this line is going to be your delta 2 hat. So directly including that wealth variable into your analysis, but it's not shown to affect consumption, it's shown to affect the marginal effect of income, if that makes sense. Good. Okay. So lots of other examples. And again, the more of these you see, the more useful you're going to find them, and the more often you're going to use them, right? So in terms of how this would show up, right, in an exam scenario, it might be something like this, right, where you're given a kind of a proposal or a question, and then you should be able to write out the regression equation that addresses that issue or that question, and it should include the correct interaction term. So a question: does the asset size of a bank impact its loan response to a change in interest rates? So again, we've got three variables there. The y variable is going to be level of lending. The x variable is going to be interest rates. And then the asset size is going to be the interaction, is going to be the z. So we're not saying that asset size might directly affect the kind of the proportion of lending, but it does affect the reaction to, say, monetary policy through interest rates. So the interaction is going to be between assets and the interest rate variable or the policy variable. So being able to identify which variables are direct and which ones are indirect. Another example: does the role of microfinance lending in alleviating poverty depend on education levels? Okay, so what is the y variable here? Well, it's going to be a measure of poverty. What is the x variable? It's going to be access to credit, microfinance lending. This is a very common question, right, in development. How much effect does access to microfinance credit have on poverty? Well, we might expect individuals, households with higher levels of education might have a greater marginal benefit from that lending. They could have a greater return on investment on average. So that line would be a little bit steeper. So we're not saying looking directly at the effect of education, but its indirect effect on the utilization of microfinance lending. So we would interact X and Z yet again. We're getting the idea here. But how about one more? Does the change in firm level output, so that's our y variable, due to a change in labor, so looking at the marginal product of labor, does that depend on the size of the firm? So we would interact firm size on, we'd have to interact firm size with labor, and the y variable would be output. So another way to say this, looking for economies of scale. Do larger firms have greater productivity? Crucial questions that can only be addressed, only be included in a regression in the form of these interactions. Okay. So once again, thinking as a researcher, which we all are researchers at this point, and you've got your data project that you're working on, again, what this does is really expands what you can do with a fairly limited data set, a fairly limited number of variables, and gives you an easily accessible way to tell a very rich story about your data generation process. It's not just X1, X2, X3 all affect Y. X1, X2, X3 affect Y, and one or more might affect how the other variable affects Y. Another way to think about it is you might have variables that are only kind of marginally attached to your product, for your project, and they might not have a real significant impact on Y directly, but you can kind of resurrect those variables in using them as only interactions, right? They can have these significant second order effect. So be able to look at your data set and think critically about which variables you might want to interact with each other and include at least one as a hypothesis test in your equation. And if they come out significant, well, that's going to be a new part of your regression. So examples, do countries in different regions react differently is the effect of your X on Y different across geographical regions? You might already have a geographical region controlled dummy variable. Does the line shift up or down? Well, now we could just say, well, is the line steeper or flatter for different regions? Do different firms react differently in recessions or expansions? Large firms versus small firms. So it's going to be that interaction second order effect. The last thing to leave you with here is linking this back to our previous discussion on omitted variable bias. If your data generation process has these indirect interactions in it, in other words, they are an actual important part of how that data is created, but you didn't think to include them, again, it's not going to be obvious, but you have omitted variable bias, right? So it puts a little bit more pressure on the researcher to, again, creatively think about how your variables relate to each other as they influence that Y variable. So hope that was helpful. Let me know if you have any questions, and we will see you next time.